All right, so let's roll most of the concepts that we've been going over together. I have here a ramp, 40-degree angle, and two masses attached by a massless rope over a frictionless pulley. So the tension, because of that, the tension between these two are going to be the same. It's the same rope, right? Now, we did this problem whenever it was flat, you know, M1, M2, so the counterweight idea, right? Something dropping and pulling the other one across. Now we're just going to do it on an angle with a ramp here. And this is very useful because you change M2 and you can either let M1 down slowly or you can pull M1 up slowly depending on whatever you need to do. If you're moving dirt or anything else off the top of a mountain, there's tons of situations and applications for this sort of idea. Now, free body diagram for M1. I'm going to have tension coming up the ramp, right? T going up the ramp like that. I have normal force going perpendicular to the surface, Fn, like this. So, you know, I've got tension coming up, normal force going out like that. And then I have gravity going down. Now, gravity going down is at some odd angle here, right, that we're not really dealing with. It always goes straight down. We need to break that into components. Now, in the last video, you learned that the component of gravity that goes down the ramp is always Fg sine theta. Okay, it's on the x-axis, but down the ramp, Fg sine theta. And into the ramp, you learned was Fg cosine theta. Cosine theta, normal force, we get to keep the same. It was already on the xy axis. All right, great. So I have my free body diagram, everything divided into components for M1, dividing the force of gravity, which goes straight down into Fg cosine theta in the y-axis and Fg sine theta in the x-axis. Yes, that's backwards from what we normally do, but that's the deal with ramps. And your theta is going to be the 40 degrees there. Let's come over and do M2. M2 just has tension going up and force of gravity going down. You know, force of gravity, mg, where the m there is going to be the mass 2, which I have labeled at 1.5 kilograms. So note the different masses. All right, system positive, system negative. I'm going to choose when the entire system rotates like this to be positive, all right, and then rotating the other way to be negative. And I've already shown this on my free body diagram for M1. I'm choosing up the ramp to be positive. It doesn't matter which way you choose, just go ahead and choose. Now, it would matter to an extent with friction. I'll get to that here in a little bit with an idea, but I'm going to make this frictionless. So I'm going to consider positive that way. So positive is going up the ramp in the x-axis, which whenever you follow that around on M2, that means down is positive and up is negative. All right, so now let's actually write in our equations for the x and y axis of M1. Remember, that's at an angle. And then just the y axis of M2 is all that I need. So just looking at this very quickly, sum of the forces in the x axis for M1 looks like it's going to be tension minus Fg sine theta equals ma. On the y axis, it looks like it's going to be normal force minus Fg cosine theta equals ma. And then in my y-axis for M2, this looks like a positive Fg minus t equals ma. And let's go ahead and let's work this problem. The end goal, I want to solve for acceleration here. All right, so I went ahead and I set up the x and y axis for both of our objects. Mass 1, our x-axis, right, was tension positive, according to how I chose system positive, system negative, minus Fg sine theta. Remember the component of gravity going down the ramp, sine theta, opposite from what we're used to with the x-axis on that ramp there. Theta here is going to be 40 degrees, angle of the ramp. The y-axis for object 1, normal force going up minus the component of gravity going into the ramp, Fg cosine theta equals ma. And then here in the y-axis of my other object, because I only had a y-axis, because of the system positive, system negative, down was positive and how I chose it there. So it's Fg positive minus tension equals ma. Now the end goal, what I'm looking for here is this acceleration and this acceleration, right? They're connected by the rope. Rewind in the video if you need to look at the free body diagram and the picture again. Now this acceleration right here I know is going to be 0, because that's the acceleration of m1 in the y-axis, and it's not flying up in the air or falling down into the earth. Now, this guy is going up and down in the y-axis, right? So this A and that A are the same. Likewise, the two tensions are the same because it's the exact same rope. So now I just need to go ahead and start trying to solve. And I'm just going to go and I'm going to start on the left, the x-axis for mass 1. And it really doesn't matter where you start, but I know this has an acceleration in it that I need, so I'm just going to start working there. So this turns into t minus, FG always turns into mg sine theta equals ma. Well, I know some numbers here, so let's go ahead and let's start plugging that in. T minus my mass, which is 2.5 kilograms for m1, 2.5, gravity 9.81, so just substituting in for g, sine, the angle of the ramp was 40 degrees, equals my mass again, 2.5 times A. And then you look at this and you say, oh boy, to solve for A here with the end goal, what I'm looking for, if I know the tension in this rope, I've got this. Notably missing here is the need for normal force. The reason that you're not going to need normal force here is because we considered this ramp frictionless, right? So I'm assuming that there is no friction in this problem. I wasn't given a coefficient of friction that I had to deal with there. So I'm not going to have to solve for normal force and the y-axis of m1 to substitute in. In fact, this y-axis I'm not going to need at all. So let's find tension, and tension is located over here. The only spot, the other spot, is in the y-axis of m2. So let's go solve for t over there so we can substitute in. All right, Fg always turns into mg minus t equals ma. Right, and now I know some numbers here. Mass of m2 is 1.5 times 9.81 minus t equals my 1.5 times A. And now let's group everything together here. So 1.5 times 9.81 comes out to be 14.715. And then I'm going to add the t to the other side and subtract the 1.5a back over here, so minus 1.5a equals a positive t. So now everything's solved for t, and that'll let me substitute in all the way over there. So I'm going to use parentheses, even though I already kind of know I'm not going to need them, but just for good habit's sake, 14.715 minus, now I can plug all that into my calculator. Don't forget my 1.5a here, 1.5a, right? And all that's in parentheses. Minus, now the 2.5 times 9.81 sine 40 comes out to be 15.764, so on there. So I substitute in for t. That's what this guy is, right? This is just all plugged into the calculator, is that right there equals 2.5a. So now I just need to group like terms. As you can see, these parentheses don't really matter, so I'm going to add the 1.5 to the other side and combine these two numbers. And then I just go ahead and divide both sides by 4, and I'm going to come out with my answer of negative 0.26 meters per second squared. Now some of you might be a little freaked out by this negative sign here. Don't be. Remember, I chose up the ramp, whenever the box was pulled up the ramp, to be positive. And what this negative sign tells me is I assumed that the box that was pulling straight down, M2, the 1.5 kilogram mass, was winning. That's why I chose that way to be positive. But in reality, it looks like it's losing, that it's actually being pulled up, and the 2.5 kilogram mass is actually sliding down the ramp. Now I did purposefully choose positive to be up the ramp because I wanted to show you that it's okay to get a negative number here. It just means that things are sliding down, or the way you might not have thought they were sliding. Now, if we had friction in here, it would change everything if you chose friction to go the wrong way, but that's another problem for a different day.